Hey, welcome back. This is Shoptalk for August 2022, and I want to do something that I hadn't done in a very long time, and that's a Ask Me Anything. If you want to know anything about how I operate the shop, about machining, about shop infrastructure, about me personally, or about one of the machines that I own, drop it down in the questions, and most likely I will answer it. I will have to sort through them depending on how much questions come in. If there are 5 questions, I can answer them all. If there are 500, I will have to kind of prioritize. The last video that I released was on the collimator lamp housings with the round profile thread, and I have a full block of video where I show grinding the tool and also answer some questions about the part in general. So let's look at that. You see this LED light bulb here? These have a standardized thread. This is an Edison thread, an E, and then it has a number. This should be a E27, means it has 26 millimeters diameter, of course. And I need to make parts with a thread like this, but not that big, but about this size. This is a test piece I did earlier, and I'm filming the intro to this video after this. So the Edison thread is a round profile thread. It has a radius on the crest and on its root. And we can achieve that only with a full profile threading tool. Imagine a regular 60-degree metric thread. You have a center line, of course, because we are civilized here. And we're drawing the cross section, of course. You have the root, you have V, you have a little bit of a land on the on top. So that's how such a thread looks in cross section. And you have 2 ways of threading this. You can either use just a V tool, thread with this. This will never give you the proper thread profile if we are really picky, because it will not form this radius on top here. We also call these, if it's a threading insert, a partial threading insert. But you can also get a full profile insert. This insert will cut the V shape and the radius on top here, or the land, or whatever you have in this thread configuration, because this insert has exactly the geometry of the gap we're cutting, including the radii. These inserts only work for the pitch they are ground for. Means you can't cut a 2 millimeter pitch thread with 1 millimeter pitch full profile insert. With the partial thread inserts, you have a little bit of a range. Well, a good amount of range. So these are threading inserts, and we have full profile inserts for metric threads from 1 to 3 millimeter per revolution pitch, and we have 2 partial profile inserts. One is 0.5 to 1.5 millimeter pitch, and one is 1.75 to 3 millimeter pitch. It's these 2 here. These don't cut the OD. These will cut the OD, and I will zoom in a second. We need such a tool to cut this round profile, because otherwise, let's say, so never without a center line. Let's say we just grind the tool like this. Yeah, this will form the thread itself, or the thread groove, the root of the thread, but it will leave these square. That's a problem. That's not the thread profile we want. The other tool we can grind looks like this. Here in red, this is full profile. This cuts not only the root of the thread, but it forms also this radius on top here. And this will leave us with this result here. And this is what we want. Now we have to figure out a way to grind this without fancy CNC grinding equipment. but a fancy surface grinder, to be honest. We have two inserts here. This is a partial profile on the left, maximum pitch 1.5 millimeter. On the right side, we have a full profile insert for a 1.5 millimeter thread. Here on the side, it's engraved 1.5 millimeter 60 degree, and this one is out of focus, 60 degree, 0.5 to 1.5. So what's the difference between those two? Well, if you look at them, it should be kind of obvious. The left one is always a compromise to do all the thread pitches from 0.5 to 1.5. That's the reason why the tip is extremely pointy and has absolutely no radius. Where the 1.5 millimeter insert, which only does 1.5, has the correct radii ground on the tip and also inside here where it forms the OD of the part. When you hold them up next together, you also notice that the partial profile insert could theoretically cut way deeper than the full profile insert, but it doesn't help you much because then you get a very, very weird thread. It looks very odd if you cut a large pitch thread and the root of the thread is sharp corner. Also, it's not good practice because you create stress riser. In overall, these work well. They're a good compromise if you want to use threading inserts, which honestly, threading inserts in general are a great invention. They're a good compromise. They work. They usually cut very nice threads, but these cut even nicer threads. They cut the OD, and also you have the advantage if you cut the thread where you don't have the counterpart, either a thread ring or the part to match it to. You can use a full profile insert and you just thread as long until the OD of the thread, you can check that with a micrometer, until that matches the tolerance of the thread you're shooting for. And then if the insert is not if the insert is ground to spec, which from most manufacturers they should be, then you should have a gauge fitting thread. It's a little bit of a risk. I wouldn't do it on a customer part, but for personal projects that's usually fine. Well, I've done it on customer project and it worked out perfectly fine too. So that's the difference between those two. Both cost about the same, but you need more of these. The thread back here is an E thread, an Edison thread. That's a light bulb thread. These threads are designed so they can be roll formed out of sheet metal, for example, for a light bulb socket. In this case, this is a machine part and we have the same round profile thread, which I recreated here in my drawing. It's an E10, and I also found, this complete drawing is reverse engineered by me, and I also found a piece of the original. This is from the GDR, Deutsche Demokratische Republik, a standard for an E10 thread, and it gives me all the necessary dimensions for both OD and ID thread. We'll come to that later. So the first course of action is to find out, can we buy an insert for the E10 thread? The answer is no. That's off the table right there. Then, next problem, what pitch does an E10 thread have? 1.814 millimeters per revolution. That's not pitch. Thinking about it, Edison thread, probably not metric, probably imperial. Turns out this is 14 threads per inch. 25.4 divided by 14 is 1.814. So that's the pitch. Do I have to change gears for this? No, I don't. Well, past Stefan didn't have the change gears. Future Stefan has, because he machined the missing 2 gears out of phenolic. Now we need a tool to cut this thread. So I figured that I can grind such a tool out of, this is just a bray. These style of tools, you will find these on Swiss lathe for usually with a profile grounded. You can either grind the profile in this orientation, or you can spin them by 90 degree and grind top down. In this case we will grind it top down. We have about 4mm wide piece of carbide here, and we can stand it up vertically on the surface grinder, tilt it for a little bit of clearance to the bottom, rotate it by 3.8 degrees because that's the pitch angle of the thread, so we don't need to grind as much clearance. We'll show some of this in CAD later, just to give a little bit of context. So let's look at the CAD model and then go to the surface grinder and grind this tool. Why are we grinding this on the surface grinder and not on the deck glass 1 tool and cutter grinder? It's made for it. Yes, it's made for it, but the surface grinder has a very accurate digital readout, which will help in the way I'm going to grind this. Okay, we're over at the surface grinder, and I found in my collection a diamond wheel with a 0.5mm corner radius, and that's ideal for the way I want to grind this tool. One last parameter is the thickness of the wheel. I could measure that, but I don't want to scratch my micrometer by measuring a diamond wheel. So I just did the old, what most grinder people do. They take a razor blade or a piece of graphite, works also very well, and you grind a slot into it with the wheel. Yes, I'm grinding steel with a diamond wheel here, but it's just the thickness of a razor blade that I'm removing here. And now I can just use either gauge blocks or the measuring microscope to check the width of the slot. And that gives me my width of the wheel, and I need that to create my tool path or my coordinates to drive the grinding wheel off. Okay, we're over at the CAD PC, and this is the shape I need to grind. I have my full radius here, or full diameter here, and 2 radii on the side that form the top of the thread. This forms the root of the thread. And this large object here is my grinding wheel. It's 3.93mm wide. That's what I determined when I ground through the razor blade. And it has 0.5mm corner radii on both sides. And I made it tangent to this path, so when I take it and I drag it, it follows the path around to a certain point, and then it falls apart because we go over the top of it, top that center. Then we would need to set a new constraint to the left radii of the wheel, and we will do that. But for now, we concentrate on the left side of this profile. What we can do now is we can put this wheel on every position we want on this radii and measure from the side of the tool we're grinding to the side of the wheel, and also from the top of the profile to the bottom of the grinding wheel. Means when I move the grinding wheel over 0.819mm, or let's say 0.8mm, I need to grind to a depth of 0.198. And when I move over to 0.9mm, I need to drop the grinding wheel or raise it to 0.134, and so on and so on. It's basically what we would do on a CNC machining when we profile a contour with a ball end mill. This root radius here is formed by the radius of the wheel. We don't have to do anything. We just move over to 0.518 millimeters and drop down to minus 0.51. And I already wrote that down in my notebook here. And then we just move on. Let's go to 0.55. What you saw me doing is I stepped the grinding wheel over in 50 micron increments. I guess that will be fine enough for grinding a form tool. And I wrote down all the coordinates in my notebook, always on an X and a C position of the grinding wheel. So let's go over in the surface grinder and grind the first quadrant of this profile. Then we'll grind the second quadrant after we hit top dead center. I have my large grinding vise laying on its side, tilted in by 3.75 degrees with some angle blocks here. So it's tilted this way. This is the lead angle of the thread. The real lead angle is 3.81, but this is probably close enough. I have the tool blank. I cut it down a little bit because the shank was ridiculous long. And I have a 5-degree angle block behind it to set my clearance to the bottom. I already surface ground the top of the tool to be my zero. I surface ground it until it cleaned up completely, and then I zeroed out my DRO, and I also side wheeled here onto the side of the tool with the diamond wheel and set my zero there. So now when I move my XY on the grinder to 0, 0, I'm exactly over the edge of this of the blank. Okay, frontal view. The diameter of the wheel, or its lowest dead center point, is exactly in line with the top of the tool here. And same for the side of the wheel. It's in line with the side of the tool where I side wheeled it a little bit. Just to clean it up. Didn't mean to remove much material here. Now I can start. My first position is to move over 0.518, and then grind down to minus 0.51. Okay, my first step in now moving the grinding wheel over a large amount to grind away all the material on this side, and this will basically already predefine both of the root shapes of this tool, which will later form the crest of the thread, but here we're grinding the root. So let's move over 5.227, and now we grind down to the same depth again. Okay, now we formed both of the radii on the side of our profile. Now we can shape the final radius that goes over the top of this profile. And for that, it's just grinding by numbers. No visual inspection needed, really. Just trusting what we did in CAD and reading the DRO. That worked way better than expected. I turned a test piece in Delrin. White Delrin is obviously perfect for non-camera part because it's hard to show any detail. But here is the counterpart. And it screws on very nicely. And it has about as much slop as the original. The OD of this thread can be between 9.53 and 9.36, and I went for the upper limit of the diameter to make it unsloppy as possible, but still be in spec. That's it. But of course, Delverin won't help us much. The real part will be stainless steel. The real part will be 303 stainless, which machine's nice, very nice in fact, but it's still stainless, not Delverin. So let's see, I have a piece of a scrap of 14305, which is 303 in the ANSI world. And we'll put a little bit of an undercut in there. Here is our threading tool. Let's turn it. I'm leaving the OD of the stock at 10 millimeters, despite the final diameter being 9.53. This is a insert that will cut the full profile, including the diameter. So we just have to go down small enough, and then it will fit. So that way we don't need a thread gauge. Not really. Yeah, and the stock is running out a little bit, but again, doesn't matter. First it's a test part, and second, this tool will cut the OD, so that's fine. Okay, now we are at the point where we're forming the OD in addition to the thread profile. As you can see, we're forming a nice radius here, and this makes me very happy. So now I can micrometer the OD, 9.85, and I put that in my DRO, and now I can just work towards 9.53. Okay. Uh, 9.55. I'm 20 micron oversized, but for first test. Oh yeah. Oh yeah. Hey. So okay. This let's get this in focus. So there is your E10 thread. Pretty much to spec, tiny bit oversized. The radii don't match 100%, so maybe the statement to spec is a little bit far-fetched, but I learned this technique of form grinding in incremental steps from Adam Demuth, Adam the Machinist on Instagram, and also Adam the Machinist on YouTube. This form grinding of this tool is a very powerful technique I learned. You can do pretty much any shape you can reach into with the grinding wheel, as long as you can draw it up. You could write a program in Excel or for a programmable calculator. I think that's what Adam has for doing this. Or you can do the cheesy way in CAD and just pulling the grinding wheel along the contour and measuring. During editing this video, it came to my mind that I didn't show how to model an Edison thread. And the answer is easy. You go in Fusion 360, you go into Create, you go into Thread, then you select Edison thread. Nope. Fusion does not come with a preset for Edison thread, which is not very surprising. So using the data sheet that I had for this thread, I modeled it myself. And when you look close at it, it's a relatively simple profile. I achieved that by using a coil primitive. You can go into Create and you have coil, which most people probably use to model springs, with the right pitch and the right wire diameter. Pushed it over, did a Boolean combine, so this body and the body of the lamp housing are molded together, they're one. And then I added a fillet in here to create the root radius. And then I did a revolve cut. That's this here, to cut the spring to length at the thread relief back in and do a nice chamfer on the end. So that's how I modeled the Edison thread. The threading tool, as I modeled it in Fusion, I just added a plane through the center of rotation and projected the contour of the thread onto this threading tool. Very easy. I didn't bother to model the clearance angles in, as when I looked down here, experience told me that when I add my helix lead angle and also some back clearance, it won't be a problem. The 1.8mm pitch is not that steep of a thread that you get into big troubles here. And it worked out perfectly fine in the end. I want to answer two questions about these lamp housings. The first question was, why did I make them in stainless steel and not brass nickel plated like the original one? And the easy answer is because the stainless steel yields more before it breaks compared to the brass that they used for the original parts. And the original parts, as shown by the examples, always snapped off in this area of the thread relief. And our hope is that the stainless that we choose will be more durable. And the other question was, how much interference fit did I leave for the lampshade to press on the body of this piece? And the answer is about 40 microns in diameter. It's a fairly hefty press fit, but this is a very thin-walled piece and it easily stretches out the 40 microns and slips on here. But it's also a very secure press fit. Then I have some additions to the shop. One is a small parts washer that I'm cobbling together currently. A good friend sent me a tool that he made and also made an excellent video about it. A little update to the parts cleaning section of my shop. Since I don't have a sink in the shop, which would be very nice, but these two rooms that I have do not have water connection nor sewage. So a parts washer was on my list of things that I wanted for quite some time now. I didn't want to buy one of those red sheet metal boxes with the fold up lid with the solder joint in case they catch fire, the solder joint melt and the lid drops down, which makes sense so you don't burn down your shop. Those parts washers usually are used with some kind of a flannel solvent. I'm not a big fan of having a large tub of solvent open in the shop. Also, the form factor of these parts washers was not exactly what I wanted. So I took I think this is a 400 by 300 millimeter and almost 300 millimeter high Euro box, storage or transport box. Bought the cheapest aquarium pump that I could get. It has a magnetic driven impeller, so it doesn't care about dirt. Bought a parts washer hose and brush. That means the hose goes through the brush and the media exits here in front where the brushes are. Added some perforated sheet metal as a floor. Currently it's just propped up on pieces of wood, but I'm gonna change that at some point. And also I don't have a switch yet, I'm just plugging it in. This is just a test setup if I like it. And the cleaning solution I'm running is the same that I use in my ultrasonic cleaner. It's Bucil Bistro G435, which is a caustic alkaline cleaner. I run it at about 10 to 15% dilution in water. Works very nicely. Degreases parts very well. It's not the right cleaner to clean tractor parts that were out in the elements for 100 years. This is for a kind of precision shop here. For example, when I have my multi-fix tool holders after a longer run of parts, it's all gunked up with cutting oil and some chips, and I want to clean them, and I don't want to have all these chips in the ultrasonic cleaner. I just use this now. And the small aquarium pump has the perfect amount of flow, it turned out. This is just enough to be able to brush off parts or tooling. And also rinse them off. For a final rinse off, a washing bottle with water, that's just fine. Then I just blow them off with compressed air to finally dry them. So that's my current solution, or my test setup for parts cleaning. I have the ultrasonic cleaner to clean very, very thoroughly, very much in-depth cleaning before I ship out parts. And this here is a rougher cleaning for pre-cleaning or for tooling. Let's say I have my vice jaws from the CNC vices. I can wash them down here, blow them off, and put them in storage if I need to. The pump is just sitting down there on the bottom of the container. It's submerged in the media that I'm running, or in the liquid that I'm running, and the sheet metal is not going all the way to the side of the container because the piece of sheet metal that I had for my test setup was too small. But as I said, proof of concept for me, if I use it at all, before I commit to something more durable. I would not buy this brush and hose again. The hose, this is more for cleaning farm equipment, less for precision parts. I would take a smaller brush, drill it through, put a 6mm hose fitting on the end, and run some 6mm polyurethane pneumatic tube as a hose, not this super heavy duty rubber hose here. The pump doesn't seem to mind either the solution itself or the chips that circulate in it. So that's my idea for parts washing if I don't have a sink in the shop. Here we are with a little project that I'm working on. This is a Toolmaker's cube. It's basically just a very square cube out of tool steel. It will get hardened and ground and eventually lapped. That has threaded holes on 4 sides. 1, 2, 3, 4. In somewhat different hole patterns. I have 2 sides with the same hole grid pattern, and I have 2 sides with different hole patterns. And what you use this for is for work holding. You can, for example, you can just bolt the part to the side of it if your workpiece has a hole in it. You can just bolt it here, you can machine it on this side, and then you can flip it over and machine a second face. And it will end that up square as this block will be. For example, if you put this on the magnet on the grinder, or if you hold the work out so it hangs out on 2 edges, you can square up 3 sides to each other using a fixture like this. Or you can use, I will make a fence that bolts to these 2 sides that you can raise and lower, and it can start flush or go above. And I will have 2 fingers with a little thumb screw that I can screw in and will hold the work against the fence, and that's also for work holding, for squaring, for intricate mill work. Things that are hard to work hold but need to be very accurate. There are many other options that you can do with these. For example, my good friend Adam the machinist, Adam Demuth, made a low profile V-block like this one. Well, he made this one and sent it over to me because he might be mildly crazy, and I really have to thank him for this beautiful piece. It's hardened tool steel, it's surface ground, and the internal V shape here is Hardmill on his DMG Mori high-speed milling machine. He has a video on making these, and please check it out. It's pretty insane. If you look at the finish in here, if you don't look careful, this is a ground finish, but it's milled with a CBN and mill. It's a really beautiful piece. And you can use this, for example, just on a magnetic chuck like this, and hold, well, a lower round piece in here. You can put a screw in here and then put a metric thread in there, which is really nice from him. And also all dimensions on this are metric too, which is very nice. So you can put something round in here and you can clamp it like this, put it on a surface grinder and dust off the end and have it very square. You could do this with a taller V-block too, but this is especially interesting for relatively short parts, or if you want, for example, to work on both sides of a part. You can hold something like this, and the hole pattern, one of the hole patterns matches up like here. You can put 2 screws in here. And now you have a very tall V-block. And you can have a part with a head, for example, that's hanging below the V-block, but has clearance against the block here. You can move it out a little bit farther if you need to. You can put it on here like this, grind a flat, and when you need a very parallel flat on the parallel to it, you just flip this block around, grind this side. We have a large and a small V in this thing. Also can be used for squaring round parts or rectangular parts too. And he also made these tiny copper pads that you just put in between the screw and your workpiece if you want to prevent marring from the screw. And the nice thing about these being loose and not part of the screw is that they're easy to exchange and very simple in use. Just like this. And since grinding requires usually not very much clamping strength, just doing this will first of all already deform such a thin-walled part, but also be plenty strong enough for grinding. Or if you have 2 of these, you can bolt one to each side of the block. So there are very many options using a low-profile V-block like this. If you don't have the option to harden mill the inside shape here to an extremely high degree of precision, I wouldn't have this option in my shop. I don't have a CNC mill that accurate. I would split this in two. I would split the block here, grind the V, then make this piece as a bolt-on part, just with 2 screws, maybe even different heights, so you get even more options and more clearance. So that's that. And yeah, that's the Toolmaker's block project. I'm making 2 of these, one for a friend, one for myself. It's a lot of hole drilling and a lot of tapping. The tapping head is doing very, very nice work here. But I will do a separate video on this. This is a very slow going project since I have paid work to do too. Same goes for my debit grinder project. Let's have a quick look at it. I have not thrown it out yet. I'm still working on it. As you can see, I painted it in the proper green color, RAL 6011 called Reseda Grün. And now I'm slowly building it back up. Also, I already made, this part needs also to go out for hardening. I already made this back plate here for the larger moment arm, which will replace the original depth stop screw in here. I have the moment arm also already roughed out. It will sit on the end of the main shaft and will have an adjustment screw and a place for an indicator here. And this will sit here. And apart from that, things are coming together. It's slow progress, but we're making progress. So yeah, that's the debit grinder project here. So I hope you enjoyed this little shop update and appendix to the lamp housing video. Thank you all for watching. Don't forget about the AMA. Drop down your questions in the comments and I'll be back.